All right, we are back to our main slides. And now let's continue on with filling in some of the details of what a probability distribution is. So, probability is going to be central to the way that we talk about data and distributions because we need to take into account uncertainty. And probability is kind of the mathematical language that we use to describe uncertainty. Using probabilities to describe things allows us to acknowledge uncertainty, things that we can't know, and that we're not looking to predict or explain things with 100% certainty. In probability theory, there's this idea of a random variable. A random variable means that we have some variable with a set of possible values that can be described by a probability distribution. So this is different than how we've mostly been using the term variable in the past, right? Usually a variable refers to a column of data in a data set. But a random variable just means that we have some bucket, right? Some referring to the variable, right? Some theoretical variable that has not been filled in yet with particular values, right? We're saying that there's many possible values that could come in and fill in what that variable is equal to. And we'll have some examples in just a moment. A probability distribution, if we want to give a more formal definition, is a list of all possible values and the associated probabilities of experiencing those values. So in the ER example, right, that we went through in the previous video, we saw that there are lots of different possible values for how many people could come into the ER tomorrow, right? It might be 90, it might be 91, it might be 100, but we can give different probabilities to those different values to say how likely we think they are to occur. That's a probability distribution. So here's your more formal definition. We've already been using the term, but here's a formal definition. All right. Probability distributions can be quite simple. So here is a classic example of a probability distribution that might have come up in high school math in algebra. So we flip a coin, and there's a 50% chance that we get a heads and a 50% chance that we get a tails, right? And these are listed as proportions. 0.5 is equal to 50%. It's just being expressed as a proportion. So this is an example of a probability distribution. What was our definition again of a probability distribution? A list of possible values and the associated probability. In this case, the possible values are heads or tails. Heads occurs with 0.5 probability or 50% chance. Tails occurs with 0.5 probability or a 50% chance. What about this distribution? What do you think this probability distribution describes? The role of a regular die, right? A six-sided die. So you can see these are all of the possible values that we could get from a die roll, and this is how likely each of them are to occur, or what the probability of each of them occurring is. So often probability distributions are taught with, simple games, rolling a die, drawing a pebble out of a bag, drawing a card from a deck, right? That's often how probability theory and probability distributions are first talked about in a lot of textbooks. And those little examples actually form the foundation for the kind of math that's used to come up with probability distributions to solve more difficult and maybe practical examples, like trying to predict ER admissions or something like that. Most of the distributions that we care about for the purpose of this class are much more complicated than these two examples that we see here. And because of that complexity, we're going to depict the distributions graphically rather than trying to list them out in exact values. The way that we generally depict complex distributions is to use something called a probability density function. And that's what you saw in the ER example when we had those smooth normal distribution lines. Those were probability density functions. There's a lot of fancy math that goes on in the background to create probability density functions, but we're not going to worry about that in this particular class. Although if you take statistics from a stats department where it has calculus as a prereq, they might actually tell you, help you learn how to some of the math that goes on behind the scenes creating those graphs. The way that you interpret a graph of a probability density function or a PDF is very similar to the kernel density plot that we saw in the appendix of our lecture 1, or even similar to a histogram, right? And we'll see an example in just a moment and spell that out a little bit more. It's important to realize, though, that probability density functions, they can have lots of different shapes, and there's lots of different kinds of distributions that statisticians have worked on developing that are going to be useful in different settings. We already heard a little bit in our example about the normal distribution, which is the one that probably gets talked about the most and used the most. So here's an example, though, of a skewed distribution. This is called the chi-squared distribution, or one version of the chi-squared distribution. And you can see that this tail on the right side is very long, and we have a short little tail over here on this side, right? So a lot of the same language we use to describe distributions of data, we can use to describe probability distributions, right? We would say this is right skewed because there are outliers over here that are likely to occur on the right side of the distribution. With PDF graphs, wherever the height is greater, the values are more likely to be observed, right? So this is the part of the distribution where it's tallest. These are the values that are most likely to be observed or most likely to occur. But kernel density plots or histograms are usually describing data that we've already collected, whereas a PDF graph is going to depict probability distributions about what, for example, is likely to occur in the future. We often use this word taking draws from a distribution, right? The data is drawn from a distribution. So this distinction is maybe a little bit subtle, and you can't necessarily tell from looking at a graph with whether it is a kernel density plot, for example, or PDF graph, unless somebody tells you, right? You might have to read the titles or the descriptions of the graph to be able to figure out. But the key distinction is that a PDF graph is about hypothetical data, right? What are the possible values for what could occur if we were to draw from this distribution, take a draw from this distribution, whereas a kernel density plot is going to describe data that we've already collected, right? That's the key distinction between the two. All right. Like I said, there's a lot of math that goes into this, and part of the reason is that when we look at a graph like this, it's assuming that we could have an infinite level of precision when we measure our values, right? And so that's going to make the math a little bit complicated. And so this is mostly beyond the scope of what we'll talk about in this particular class, but just to give a very brief preview of how these PDF graphs work, the area underneath the line of the graph is always going to be equal to exactly 1. In other words, there's a 100% chance or a probability of 1 that if we take a draw from this distribution that we'll get some value that is underneath this graph, right? And so that's why the area is always going to equal to 1. And if we want to figure out, well, what is the probability of getting a value within a certain range? For example, in this case, maybe it's a value between 0 and zero point 0.7. Well, then we have to calculate what is the value of the area under the graph, just this portion, right? And again, all of the area under the graph is going to be equal to 1. So we want to know just this portion. Well, maybe this is 0.2, right? In other words, maybe there's like a 20% chance that we get a value between 0 and 0.7. So calculating the area under a portion of the graph requires calculus, which is why we're not going to go into detail in this class on how to do that. But that's the kind of math that's going on behind the scenes in a lot of stat software when it's telling us something about how likely particular values are to occur, or when it's generating a confidence interval, right? Which is implicitly thinking about 95% of the time something occurs. Well, we want to get 90%, 5% of the area under the graph, for example. So when we talked about distributions the last few weeks, we maybe didn't always use that word, but we were talking about data that had already been collected. And again, the key distinction today with probability distributions is that they describe a theoretical process from which we get data. They're not describing data that we've already collected. So here's another example. If we write out the theoretical probabilities for possible outcomes from a coin flip or from a die roll, we're talking about a probability distribution. So that's what we saw a few slides ago. It was telling us how likely a heads is to occur, how likely we are to get tails, how likely we are to get a 1 or a 2 or a 3. That's a probability distribution. If we flipped a coin or rolled a die 20 times and recorded the results, now those results are a distribution of data, which we might depict with something like a histogram. So just to distinguish here between the probability distribution, how likely each value is to occur, versus a distribution of data that we've collected, right? How likely or how often each value did occur, right? So this is probabilistic, what's likely to happen in the future. This is what's already occurred. We flipped a coin 20 times. here are the different values that we got. Another way to think about this distinction is that for a distribution of data that we've collected, we each observation was theoretically drawn from the probability distribution. In other words, we have 20 coin flips and we recorded the values, and each of those coin flips was one realization of this theoretical process, the probability distribution that we outlined above. So going back to our ER example, if we have a distribution, a probability distribution that describes how likely we think we'll get various numbers of patients visiting the ER on a given day, we're looking at a probability distribution. Again, this is how likely different things are to occur on a given day or going into the future, right? That's a probability distribution versus data of what has already occurred. That's a distribution of data, not a probability distribution. Many of the same statistics and words are going to be used to describe the two types of distributions, a probability distribution versus a distribution of data. And so because of that, it's often not going to be super obvious what the distinction between a probability distribution and a distribution of data is. That's why I spent so much time in this lecture trying to explain exactly what that difference is. And so, for example, probability distributions are often going to have a mean and a variance, and we'll have to calculate them a bit differently than we do for a distribution of data. But those are two terms that we've been using throughout the semester now to describe a distribution, calculating the mean of the distribution, the variance of the distribution for a particular variable. We can use those same descriptors for a probability distribution, although the way we calculate them, like I said, has to be a little bit different. So there's a lot of overlap between these two concepts, a probability distribution and a distribution of data, a lot of common language that we're going to use. But the key thing, again, that I want you to remember is that one is about projecting into the future, and the other is about data that we've already collected. All right, let's look at some more probability distribution. So we already learned that there's something called a normal distribution. This is probably the most commonly used probability distribution in statistics. And here's a picture of a normal distribution. All normal distributions have this basic bell curve shape, but a normal distribution could be shifted to the left, to the right. It could be squeezed down. It could be expanded, right? There's different shapes that it can take on, and I'll show you that in just a moment, right? So these are all different versions of the normal distribution. They all have the basic bell curve shape that we saw on the previous slide, but as you can see, it can be different heights, and it can be moved to the left or to the right. And all of these are the normal distribution. So one term that people use sometimes to describe the normal distribution is that it's actually a family of distributions. It's not a single distribution. It's a family distribution of distributions because all four of these are examples of different normal distributions. And there are many more normal distributions, an infinite number of normal distributions that we could identify because there's a different normal distribution for every possible real number there is, because the normal distribution can take on any mean and it can take on any positive variance. So if we can name a number and plug it in as the mean, then we can identify a new normal distribution, right? So here we just have two examples of different means that the normal distribution could take on. We can have normal distributions with a mean of 0 or with a mean of -2. But of course, we could have plotted one for +2, for 3, for 4, for 4.5, etc. So anytime somebody mentions the normal distribution, a fair question would be to ask, which normal distribution are you talking about? And the way that they could answer that question is to give the mean and the variance that they have in mind, right? So once I've said the mean and the variance of a particular normal distribution, then I know which normal distribution is being talked about, right? So normal distribution with a mean of 0 and a variance of 0.2. That's this tallest normal distribution. Or the normal distribution with a mean of 0 and a variance of 1. That's this mid-height normal distribution here. And again, the point is that they all have this basic bell curve shape, but it can be flatter or it can be taller. And again, it can be moved to the left or the right. But notice that in all of these cases, the distribution is symmetrical. It's not like any normal distribution will have a skewed distribution. You can't have a normal distribution with a skewed distribution. It's always going to be symmetrical and have this one of these basic shapes. Okay. Couple more things we should know about the normal distribution. So one of them is we have some rules of thumb for how likely we are to get different values from a normal distribution. So right here in the middle of this graph, we have mu. And if you'll recall, mu is usually used to describe the mean of a population. So as we saw in the previous slide, with a normal distribution, we can change what the mean is. We can change the value of mu. But whatever value we pick, whether it be 0, -2, +10, it's always going to be the middle of the distribution, always going to have this shape. If we go one standard deviation above the mean, right, which the standard deviation is represented with this Greek letter sigma, and we go one standard deviation below, then that range being within one standard deviation of the mean, this part of the distribution is going to represent something that is going to occur 68% of the time. So in other words, if we want to know, taking a single draw from a normal distribution, how likely are we to get a value within one standard deviation of the mean? Well, 68% of the time, we're going to get a value within one standard deviation of the mean. Just like if we roll a die, 1/6 of the time, we're going to get a value of 6, right? If we take draws from a normal distribution, 68% of the time, we're going to get a value within one standard deviation of the mean. The most important thing to remember from this slide is that 95% of the time, we're going to get a value within two standard deviations of the mean. And this is going to be important in particular because we often use this rule of thumb when we're constructing confidence intervals. If you'll recall, when we learned about confidence intervals before, we were talking about 95% confidence intervals. And so it's important to know, at least if we're working with a normal distribution, that if we want to construct something, a range of values that we can say 95% of the time we're going to get something within this range, then we can just go out two standard deviations in both directions from the mean. So if we have a mean of 10 and a standard deviation of 10, then going two standard deviations from the mean, this is going to be 40, right? So again, if the mean is 20, one standard deviation from the mean, 30, two standard deviations from the mean, 40. Again, the standard deviation being 10, the mean being 10, one standard deviation below the mean, 10 minus 10 is 0, and this would be a -10, right? So we will probably go over more examples of this in the future, but the idea is that being within two standard deviations of the mean is something that will occur 95% of the time when you're doing draws from a normal distribution. Finally, if we go out three standard deviations, well, almost always, 99.7% of the time, when we take a draw from the normal distribution, we'll get a value within three standard deviations of the mean. And again, just to put a fine point on this, we can grab different values of the mean. We can choose different values for the variance. And regardless of which of these values we choose for the mean and the variance, these rules on the next slide are always going to apply. In other words, it might change what it means to be two standard deviations above the mean, right? That might be 2 units above the mean. It might be 10 units above the mean, but it's always going to be the case that if we're looking at a normal distribution, that 95% there's a 95% chance that we get a value within two standard deviations of the mean when we take a draw from the normal distribution. All right. Like I said, this will be an important building block for confidence intervals, which we're going to talk about in more detail in future lessons. And we're going to use this rule of standard deviation times 2 in that context. So we'll see that again. All right. Last slide from the main lecture slides. What about something called the standard normal distribution? All the previous slides just talked about the normal distribution. What is the standard normal distribution? Well, the standard normal distribution is the normal distribution with a mean of 0 and a standard deviation of 1. Whereas the normal distribution can take on all kinds of different values for the mean and the variance, the standard normal distribution is a particular version of the normal distribution, the one where the mean is 0 and the standard deviation is 1. And you can see that we actually had that as this middle height normal distribution that was centered at 0 on the previous page. Notice that here it's saying variance instead of standard deviation. But if you square 1, what's 1 squared? Well, 1 squared is 1. So the variance of 1 is also equal to having a standard deviation of 1. In other words, anytime you have a variance of 1, you also have a standard deviation of 1, because if you square 1, you get 1. If you take the square root of 1, you get 1. So those two statements are equivalent in this particular context. Normally, the variance and the standard deviation are not equal to one another. But if the standard deviation is 1, then the variance also happens to be 1. Okay, so the standard normal distribution is the normal distribution with a mean of 0 and a standard deviation of 1. And so if we apply these rules that we had from the prior slide, you can see they've used more decimal places here now. So it's a little bit more, these percentages are slightly different than we saw on the previous slide. But we can see that this bottom row, which is labeled Z, gives us the standard normal distribution, right? In other words, the mean is 0 and the standard deviation is 1. So going up 1 unit above the mean, 1 standard deviation above the mean gives us a value of 1. 2 standard deviations above the mean gives us a value of 2. 2 standard deviations below the mean gives us a value of -2. And one of the reasons this is called the standard normal distribution is because it's related to this idea of standardization that we learned about in lecture 2. You might recall that we said that standardization was a way to transform a variable, right? Where we changed the variable so that it had a mean of 0 and a standard deviation of 1. Well, that's exactly what the standard normal distribution looks like. It has a mean of 0 and a standard deviation of 1. So you can see at the top above the horizontal line, we have values that are different, right? It looks like they're measuring things in centimeters. And so you can see that the original distribution had a mean of 135 and a standard deviation of what's 150 minus 135? I think that's 15, right? A standard deviation of 15 centimeters. So we took these original values, we standardized them so that there would be a mean of 0 and a standard deviation of 1. And now if we relabel it with these numbers at the bottom, we have the standard normal distribution. All right, that's it for today. I realize this lecture is covering some concepts that are pretty abstract, right? We started with some words like unimodal, bimodal, skew, tails, right, to describe distributions. Hopefully that is a little bit more tangible and easier to work with. But the idea of probability distributions is very abstract. It can be kind of hard to wrap your mind around. And we're going to talk about it more in future weeks. When we talk about standard errors in lecture 6, those are going to be describing probability distributions, and they're going to be the building block that we use to create things like confidence intervals or to conduct statistical significance tests. So what we learned today about probability distributions is really a foundation for practical tools that we're going to use and dive into in more detail in the future. So if some of this was a bit abstract and a little bit hard to understand, don't worry about that too much. We really just wanted to go over some of the foundations of that will be used for tools, for very practical tools that we'll use in the future. And I think it's useful for you to learn some of this foundation, even if some of it goes over your head the first time you learn it. But we will take some of this information about probability distributions and put it to very practical use in the future. So look forward to that in future lectures. And hopefully you learned something today about probability distributions.